Assalamualaikum warahmatullahi wabarakatuh and greetings to our Madam Suhada. Today, our group will be doing Assessment 3 Group Presentation video. We will be answering two questions, which is F from the question 1 and A from question 2. This group consists of two members. The first one is NORLILYANA, AYUNI, JASMI, and the second one is I, SITI, BAHIYAH, Salleh. We are from CDCS 2495C. Now, let's start with the question 1F. The question is a theorem 10. If M divides the order of finite abelian group G, then G has a subgroup of order M. From theorem 9, we can think of G as being the direct product of cyclic subgroups of order P1 to the power R1, P2 to the power of 2, up to Pn to the power Rn, where not all primes Pi needs to be distinct. Since P1 to the power R1 times P2 to the power R2 and so on up to the Pn to the power Rn is the order of G, then M must have the form of P1 to the power S1, P2 to the power S2 and so on up to Pn to the power Sn, where Si is greater than or equal to 0 or less and less than or equal to Ri. By a previous theorem, Pi to the power Ri minus Si generates a cyclic subgroup of Pi to the power Ri of order equal to the quotient of Pi to the power Ri divided by the greatest common divisor or GCD to the power Ri and Pi of Pi to the power Ri and Pi to the power Ri minus Si, but the GCD of Pi to the power Ri and Pi to the power Ri minus Si is Pi to the power Ri minus Si. Thus, the Pi to the power Ri minus Si generates a cyclic subgroup of order Pi to the power Si, recalling that the notation or angle brackets and denotes the cyclic subgroup generated by A. We see that the product of angle brackets P1 to the power R1 minus S1, angle brackets P2 to the power R2 minus S2, and so on to the angle brackets Pn to the power Rn minus Sn is the required subgroups of order M. Next is the example. We let the G is Z18, the cyclic subgroup integer modulo 18 under addition. Now, step 1 is to finding the order of G. The order of G is 18. Step 2, the divisor of 18 is 1, 2, 3, 6, 9 and 18. According to the theorem 10, G must have a subgroup. Step 3, we will identify the subgroups. Subgroup of order 1 is 0 generated by 0. Subgroup of order 2 is 0 and 9 generated by 9. Subgroup of order 3 is 0, 9 and 0, 6 and 12. It is generated by 6. Besides, subgroup of order 6 is 0, 3, 9, 12 and 15 generated by 3. Second last subgroup of order 9 is 0, 2, 4, 6, 8, 10, 12, 14 and 16. It is generated by 2. Lastly, the subgroup of order 18 is G itself, generated by 1. Hence, each group has specific order confirming the theorem 10.
Assalamualaikum warahmatullahi wabarakatuh. I'm NORLILYANA BINTI JASMI and I will present about question 2. The question 2 is, let H be a subgroup of a group G, then left coset multiplication is well defined by the equation AH BH equal to ABH if and only if H is a normal subgroup. Okay, first of all, let we look at theorem 1. Let H be a subgroup of a group G, then left coset multiplication is well defined by the AH BH equal to ABH if and only if H is a normal subgroup. Okay, proof. Suppose that ABH equal to ABH does give a well-defined binary operation on left coset. Let A in G, we want to show that AH and HA are the same. Let X in AH, choosing representative X in AH and A prime in A prime H. We have X hash A prime H equal to X A prime H. Using our assumption that left coset multiplication by representative is well defined, we must have x a prime equal to hash in hash, then x equal to hash a, so x in hash and a hash subset to hash a. We leave the symmetric proof that hash a subset of a hash. Okay, proof. Suppose that AB hash equal to AB hash, thus give a well-defined binary operation on left coset. Let A in G, we want to show that A hash and hash A are the same. Let X in A hash, choosing representative X in A hash and A prime in A prime hash. We have X hash A prime hash equal to X A prime hash. Using our assumption that left coset multiplication by representative is well defined, we must have x a prime equal to hash in hash, then x equal to hash a, so x in hash and a hash subset to hash a. We leave the symmetric proof that hash a subset of a hash. Okay, next I will move to the example. The question states that let G equal to Z4 and hash equal to 0, 2. Prove that the left coset multiplication is well defined for the cosets of hash in G and show that hash is a normal subgroup of G. Okay, step 1 is we need to show that the left coset multiplication in G is well defined by defining the left coset of hash in G. Let G equal to Z4, which is 0, 1, 2 and 3, and hash equal to 0, 2. A coset of hash is defined as A hash equal to A plus hash mod 4, where A in G. Next, we compute the first coset, which is coset 0 hash, where 0 plus 0 mod 4 is equal to 0 and 0 plus 2 mod 4 is equal to 2, and this solution is equal to hash which is 0, 2. Okay, the next coset is 1 hash. We use the same method, which is 1 plus 0 mod 4 is equal to 1 and 1 plus 2 mod 4 is equal to 3. Follow with coset 2 hash, which is 2 plus 0, 2 plus 2 equal to 2, 0 equal to hash. And coset 3 hash equal to 3 plus 0, 3 plus 2 equal to 3, 1. For this case, we need to stop at 3 hash since the Z4 is 0, 1, 2 and 3 only. Okay, to determine the distinct cosets, we focus on whether each coset contains entirely different elements from previous cosets, such as 0 hash is equal to 0, 2, 1 hash is equal to 1, 3, 2 hash is equal to 2, 0, which is identical to 0 hash, and 3 hash is equal to 3, 1, which is identical to 1 hash. Thus, we can conclude that the distinct coset of hash in G are 0, 2 and 1, 3. Next is by checking coset multiplication is well defined. We now check whether multiplying two cosets give consistent result. The multiplication is defined as A hash B hash equal to AB hash for AB in G. Let's verify this. The first one is multiplication of 0 hash times 0 hash is equal to 0 hash 0 hash, equivalent to 0 times 0 bracket hash. The result is 0, 2, which is hash. So 0 hash times 0 hash is equal to 0 hash. Proceed for the next, which is multiplication of 0 hash times 1 hash. Okay, 0 hash times 1 hash is equal to 0 hash. 1 hash is equal to 0 times 1 hash. We factorize the hash and we got 0 times 1 hash equal to 0 hash equal to 0, 2. The last part for multiplication is multiplication of 1 hash times 1 hash is equal to 1 times 1 hash equal to 1 hash equal to 1, 3. Thus, the multiplication is GZ4 with hash equal to 0, 2 is well defined by A hash B hash equal to AB hash for AB in G. Okay, the second step is by checking the normality of hash. To prove that hash is a normal subgroup, we need to verify that A hash equal to hash A for all A in G. For each A when A equal to 0, for left coset, 0 hash equal to 0 plus 0, 0 plus 2 equal to 0, 2. Why? The right coset is hash 0 is equal to 0 plus 0, 2 plus 0 equal to 0, 2. Therefore, 0 hash equal to hash 0. Okay, when A equal to 1, on left coset, 1 hash is equal to 1 plus 0, 1 plus 2 equal to 1, 3, while on the right coset is hash 1 is equal to 0 plus 1, 2 plus 1 is equal to 1, 3. Therefore, 1 hash is equal to hash 1. Where A is equal to 2, on the left coset, 2 hash is equal to 2 plus 0, 2 plus 2 is equal to 2, 0. And on the right coset is H2 is equal to 0 plus 2. 2 plus 2 is equal to 0. Therefore, 2H is equal to H2. Okay, the last one is when A equal to 3. On the left coset is 3H is equal to 3 plus 0. 3 plus 2 is equal to 3, 1. While on the right coset is H3 is equal to 0 plus 3. 2 plus 3 is equal to 3, 1. Therefore, 3H is equal to H3. Okay, the conclusion is since AH is equal to HA for all A in G, therefore H is a normal subgroup of G.